Hi, I'm Yang, and today I'm going to be talking about vertex sparsification for edge connectivity in polynomial time. To start, let me introduce the problem of vertex sparsification more generally. The problem of vertex sparsification asks, given a graph G, which has vertices V and edges E, and some terminals T, which are a subset of the vertices, the goal is to find a smaller graph H that also contains those terminals T that approximately preserves some property amongst vertices in T. This property that can be preserved can be several things. Examples that have been studied in the past include spectral vertex sparsifiers, also known as Schur complements of graphs. And these objects preserve electrical properties between the vertices in the terminal set T. Flow sparsification asks to preserve multi-commodity flows where the demands are supported on the terminal set T. And cut sparsification asks to maintain edge connectivity between subsets of the terminals T. The goal of a vertex sparsification problem is to prove that you can construct a graph H whose size depends only on T, and the smaller the dependence on the size of T, the better. Throughout this talk, we're going to let K denote the size of T. In this talk, we're going to be focusing on vertex sparsification for edge connectivity. So let me just formalize that problem. In vertex sparsification for edge connectivity, we want to preserve the min cut in the graph G between S and T minus S for any subset S. So for any partition of the terminal set into a subset S and T minus S, you want to preserve the min cut in some way. The min cut here is defined as, between S and T minus S, is defined as the minimum over cuts in the original graph G whose restriction to the terminal set T is just S and T minus S. So it's the min over all A intersect T equals S of the number of edges between A and B minus A in the original graph. A mimicking network is defined as a graph H that preserves this cut exactly. What's known about mimicking networks is that the size of H is at most 2 to the 2 to the K, so doubly exponential in number of terminals. And it's known that there exist graphs G where the number of vertices in each has to be at least 2 to the K, but nothing really is known about closing this gap. If you ask for approximate notions, I just want to maintain every cut to a 1 plus epsilon factor. Very little is known in general. No lower bounds are really known that are better than linear in K, and upper bounds, I don't know of anything really better than exponential or doubly exponential. So it's a kind of wide open problem. In this work, we focus on the problem of C edge connectivity. This is actually a more restrictive version than even the 1 plus epsilon approximate. So here we should think of C equals something like 10, like a small constant. And the goal is to construct a graph H that preserves min cuts exactly as long as they're in most C. In other words, we want to preserve the value of min of C in the min cut. So we want to preserve small connectivities, and if the connectivities are large, we don't really care. Let me just give a little bit of broader motivation for why study vertex sparsification in general. In general, designing vertex sparsification and efficient algorithms for constructing the vertex sparsifiers, it leads to efficient graph algorithms for a variety of problems. Efficient algorithms for constructing Schur complements have led to very beautiful and simple Laplacian solving frameworks, as well as data structures for dynamic electrical flows. Vertex sparsifiers for lengths and cuts have given dynamic data structures for transshipment and max flows approximately. Along these lines, recent works have used C edge connectivity mimicking networks as defined on the previous slide to give dynamic pairwise C edge connectivity in m to the little o of 1 amortized time for constants C. So C equals 10, we can add edges to a graph, delete edges to the graph, and query C edge connectivities in amortized m to the little runtime. Additionally, Vertex Sparsifiers for C edge connectivity can be used to solve the subset C edge connectivity problem, which is to find the smallest cost subgraph that makes all pairs of terminals in T C connected. Another point I wanted to discuss about C edge connectivity vertex sparsifiers is why is it important that we want to maintain the min cut between all partitions S and T minus S as opposed to the min cut just between pairs of terminals? The critical reason is because of the following lemma. If H is a C connectivity mimicking network of G, and we add an edge between a pair of terminals, then H is still a C edge connectivity mimicking network of G as long as we add the edge E in. So H with the edge E added is a C connectivity mimicking network of G with the edge E added. This is not true for the pairwise definition. The intuition is that a pair of vertices might have several min cuts. And if you just preserve one of the min cuts, then adding this edge E, it could cross that one min cut that we're seeing, and then the size goes up. So that's really the big reason why we study maintaining the connectivity between S and T minus S for all subsets S, as opposed to just pairwise. In particular, for the dynamic data structure design, it is important to work with the all subsets definition, because you want to dynamically maintain the graph H. So when G undergoes an edge insertion between terminals, then we can update H efficiently just by adding in the edge E itself. Now let me state the results of this work. Previous works have given C edge connectivity mimicking networks with K times C to the fourth edges, and they were constructed in time m C log n to the O of C. Our results construct mimicking networks with KC cubed edges, so less edges, or KC cubed times polylog number of edges in randomized polynomial time. So notice that if C is at least log K or log n, then the previous works did not run in polynomial time. However, our algorithm does run in polynomial time regardless of the value of C. And it's worth noting that the results of this work have been extended to hypergraph settings. Before going on into the proof, let me just state a couple of future directions that I find to be very interesting. I think the most important future directions are to improve the runtime to m times poly c. The runtime of this work is just polynomial in the number of edges, just poly m. But I think m times poly c would be a big deal because that's kind of linear in m and polynomial in c. And optimistically, if that algorithm could be made dynamic, then you could get dynamic C edge connectivity and amortized O tilde poly C time. This would greatly improve over the current bounds, which are m to the poly C times little o of 1. So it's m to the little o of 1, and then the exponent has a polynomial dependence in C. So it would really be a big improvement if this all went through, but currently the runtime of the algorithm presented in this work is just polynomial in number of edges. Now let me go over the proof. The first step in the proof is to reduce to the case where all terminals have degree 1. We do this at the cost of increasing the number of terminals by a factor of C. So this accounts for one of our 3 factors of C. Our bound is KC cubed. Basically, the way this is done is you assume that every terminal has degree n most C because we only care about C edge connectivities. Then if a terminal has some number of edges out of it, you kind of just treat each of those edges itself as a terminal. And so what happens is the number of terminals now has gone up by a factor of C, but now all the terminals have degree 1. Our main lemma is that if all terminals have degree 1, then we construct a C edge connectivity mimicking network with size of t c squared edges, or size of t c squared times polylog number in polynomial time. This implies our main result of this work, which is k times c cubed edges in the mimicking network, because we've increased the number of terminals by a factor of c. The proof of this main claim has 2 steps. The first step is to use ideas from matroid theory, or representative sets of matroids, to show a bound of t, c, c plus d, where d is the largest number of vertices, number of terminals on the smaller side of a min cut of size of most c. So here, it's like a max over the min cut between s and t minus s in the graph G, most c, of the smaller of the 2 sides. Now, our goal is going to be to reduce the value of d by partitioning the graph. We're going to reduce to the case where d is O of c, or d is O of c times polylog n by using a Sparsest Cut algorithm. So the d is O of c bound can be done existentially, but not efficiently. But we can reduce to a case where d is O of c polylog n by calling a Sparsest Cut algorithm, and that can be done efficiently. Let me start by discussing the second part, the recursive partitioning. So how do we reduce this value of d, which is, as a reminder, it's the largest possible value of the number of terminals on the smaller side of a small cut. To recursively partition the graph, we require the following lemma. Given a graph G with some vertices v and edges e, and some subset A of the original graph, so A is a subset of V, and terminals T, we want to if you partition the graph G into A and V minus A, and then you add some terminals, you add all endpoints of the cut edges as terminals, then if we recursed on the vertices A and V minus A separately, built mimicking networks for them, and then took their union plus all the cut edges, then we'll have a mimicking network of the whole graph. So that's a lot. Let me try to give an example. So let's consider the following graph with 4 terminals marked in red. This graph has a sparse cut, so let's imagine partitioning the graph along the sparse cut into 2 halves. There's one cut edge, and we want to add both the endpoints of the cut edge as terminals. Now we have 2 separate sides, each with 3 terminals. We're going to recurse on both halves and build a mimicking network on both of them. The way it's done, you can just turn it into a triangle. Now you add back in the cut edge, and you can show that this resulting graph is a mimicking network of the original graph. Okay. So now the algorithm is in general going to be simple. We're going to find a sparse cut for some definition of sparse. We're going to partition the graph along that sparse cut, add in the endpoints of the cut edges as terminals, and just recurse until we can't anymore. The definition of sparse cut we're going to use is that while there exists a cut A V minus A with the most C edges, and the number of terminals on the smaller side is at least 3 times C, then we're going to partition along that cut and then recurse on both sides. It is easy to show that if you do this, then when we're finished with the procedure, at most O of T total terminals will have been added to the graph. So there's still O of T terminals in the graph. Now we just build the mimicking network on all the subgraphs, and hence we've reduced to the case where D is almost 3C. Now, this is inefficient because it's unclear how to check whether there's a set A with and most C cut edges, and the smaller side has size at least 3C. To do this efficiently, we're going to use a Sparsest Cut algorithm to get an approximation for our partitioning. Now, the algorithm is going to undergo a small change. While there exists a set A, such that the ratio of the smaller side to the number of cut edges is at least C times log n to the 3 halves. We're going to partition along A, B minus A, add the endpoints of E, A, V minus A as terminals, and recurse on the subgraphs. So if there exists such a sparse cut, then you can use a root log n sparse cut approximation algorithm to find an A where the sparsity of the cut is at least log n instead of log n to the 3/2. And you can prove that if you partition recursively with cuts that have sparsity log n, then there's the most O of t total terminals at the end of the procedure. And through this, we reduce the case where d is at most c times log n to the 3/2. So now that we've finished the recursive partitioning scheme, the next part to discuss is how to prove a bound of O of t times c plus d. Once again, d is the number of terminals on the smaller side of a small cut. We're going to do this with matroids and representative sets, but it's still useful to set up some kind of framework to apply this with. We're going to call an edge E essential if contracting the edge E affects some min cut. More precisely, we call an edge E essential if for some cut S, some subset S, the min cut between S and T minus S goes up when we contract the edge E in the graph. This is equivalent to saying that the edge E is in every S T minus S min cut for some subset S. It suffices to show that there's a most O of t times C plus D essential edges. The reason being that if there's some edge E that's not essential, you can just contract it, and it's obviously a C edge connectivity mimicking network. So you keep contracting edges that are not essential until all the edges are essential. So if we were able to show that there's a most T times C plus D essential edges, then we're done. So we're going to use matroids and representative sets to show this bound on the number of essential edges. For the purposes of this talk, we can think of a matroid as just a matroid is an object whose ground elements are vectors over some finite field, and independent sets in the matroid are just collections of vectors that are linearly independent. For a matroid M and some collection of independent sets I, we say that a subcollection I star is a representative set for I if for all independent sets X, such that there exists a Y in I that is disjoint from X, and X union Y is independent in M, then there must exist a Y prime in I star that has the same property. It's disjoint from X, and X union Y prime is independent in M. A classical theorem of Lovas and more recently Marx says that if M is a direct sum matroid, and all the MIs are representable over some finite field, meaning that they can be represented as vectors and linear independence. And MI has a ground set SI, and I is a subset of is a collection of independent sets, which is just a subset of picking one element in the ground set of each matroid. Then we can find an I star that's a representative set whose size is the most the product of the ranks. While I'm not going to give the details for how to apply this, I'm at least going to state kind of intuitively what's going on. The idea is that we construct a matroid M, which is the direct sum of 3 matroids. The idea is that M1 encodes the cut edges, M2 encodes the terminals that are on the larger side of the cut, and M3 encodes the terminals that are on the smaller side of the cut. The key claim is that in this construction, an edge E must be in the representative set I star if the edge E is essential. Thus, by the previous theorem, the size of I star is in most the product of the ranks, which is in most C times K times D. The rank of M1 is in most C because M1 encodes the cut edges, which there's a most C of them. M2 is the terminals on the larger side of the cut, which there's a most K. and M3 encodes the terminals on the smaller side of the cut, which there's in both D. So we get a bound of C times the number of terminals times D. The reason our final bound differs a little bit from this is to formalize this, you must actually work with vertex cuts instead of edge cuts, because vertex cuts end up more naturally corresponding to certain matroids called the gamoids. And that's the matroids we actually use in the construction piece. To wrap up, this work gives C edge connectivity mimicking networks with KC cubed edges, or KC cubed times polylog edges in randomized polynomial time. If C is at least log n, this improves over KC cubed, which ran in M times C log n to the O of C time, which would not have been polynomial time for large values of C. The algorithm has two main steps. We first recursively partition to reduce the smaller side of the small cuts. This is efficient up to polylog factor losses due to Sparsest Cut approximation algorithms. And in the second step, we open up the matroid theory or representative sets constructions to achieve a smaller mimicking network when the smaller set is guaranteed to only have a few vertices. The main open problems are improving the runtime to M times poly C, or dynamicizing that construction to give better dynamic algorithms for C edge connectivity. And yeah, that's the talk.